Okay, thank you. Thanks to all of you for coming, and it's a great pleasure to be here and to have the opportunity to present these lectures. So, yeah, the subject that I chose is indeed entitled Exotic Lattices and Simple Locally Compact Groups. In fact, so what I've been studying locally compact groups for some time now, and especially the simple ones, the simple non-discrete ones. But in fact, my initial motivation to look at the groups is because they are useful to construct interesting discrete groups, and that's the story of my lectures today, and for the coming lectures too. And this is also the specific topic is the work of Marc and Shahar Mozes on the construction of virtually simple lattices in the product of two trees. And yes, I'll give some details, and also I'll explain some of the details in a slightly different way than they did it originally, about 20 years ago. And for a start, I'd like to to present you two groups. Gamma 1, it's a 4-generator group, A, B, X, Y, with the following presentation. A, X inverse, B, X inverse, A, Y inverse, B, X, Y inverse, B, X, B, Y inverse. So it's a 4-generator group with 4 relations. And this group has a friend which looks the same, 4 generators, and then you start copying the relations, but you make 3 small mistakes. So here's the first mistake. Here's the second mistake, and that's the third. Okay, so these groups look similar just from the point of view of their presentation, but what I'd like to explain is that they are very different. And so gamma 1, so properties. So gamma 1 appears was defined and studied by Jacob Stix and Alina Vodina. And among other things, they show that gamma 1 is hereditarily just infinite. So I should explain this term. So just infinite, this means that every proper quotient is finite. Okay? Just an example, and the group is infinite. But group is infinite. The simplest example is Z, infinite cyclic group. Hereditarily means that this property of the group is inherited by finite index subgroups. Okay, so this means property inherited by 4 finite. Another property of gamma 1 is that it's not virtually linear. And then, so what you can deduce from these two is that it has finite, so gamma 1 has fab.
Finite abelianization.
Oh,
So all finite index subgroups have finite abelianization.
quickly give an example of a group that's just infinite but not very terribly.
That's an exercise. So Z is just infinite. Z squared is not. But now find a finite extension of Z squared that's just infinite, and then yeah, you have an example. Another example is take a simple group, so that's just infinite. Now if you take the Reed product of a simple group with a cyclic group of order 2, that will be an example. So, example of just infinite of a just infinite group is not HJI. S with C2, S infinite simple. So it's really stronger. And gamma 1 has also the nice feature of being linear over a field of characteristic 3. So in particular, it is readily finite. So that's a list of properties satisfied by gamma 1. What about gamma 2? Gamma 2 maps onto the infinity. The infinite algebra group has T S squared E squared. And this you can check with me by the following assignments. A maps to S, B maps to S, X maps to STS, and Y maps to T. Yeah. Okay? So in particular, gamma 1 and gamma 2 is not fab. And more importantly, gamma 2 is not readily finite. Okay, so the morality of this introduction is when you work with such groups, you should rather pay attention and not make a mistake when
Is it possible to say quickly why gamma 2 is not residually finite?
what do you say?
Why is gamma 2 not residually
That's it will require a couple of hours. I mean, at the end of my maybe
No,
my
it's not
third
possible
lecture.
to say quickly.
Yeah, I could.
No.
It's
fine.
the goal.
As long as it's not
It's
supposed
so-
to be obvious.
the
It
goal-
wasn't obvious.
so-
to me, I wanted to check.
Explaining this, so this will be a goal, one of the goals. Of my lectures, probably by lecture 3, but we'll understand that. Okay, So, but for now, this introduction is kind of the motivation for me to introduce a collection of groups, a class of groups, which contains gamma 1 and gamma 2, but it is a bit larger. But I want to define this class using the specific geometric features of gamma 1 and gamma 2. And as you can guess, so gamma 1 and gamma 2 are both subgroups of the product of the automorphism group of two copies of the same tree. So T4 is a 4-valent tree. So they act freely and transitively on vertices. Okay, so if X is the product of the two trees, okay, I can look at the quotient complex. Right? So this is a square complex with one vertex, 4 edges, and 4 squares. Right? And the fact that this is a product of two trees, it's detectable on the level of the quotient by the key property that the link, moreover, the link at the vertex is isomorphic to the complete bipartite block. Okay. So this is my excuse to introduce a class of complexes, which I'll call BMW complexes. The BMW complex. So BMW stands for Virgil, Mozes, and Wise. So they kind of independently pioneered their study. So a BMW complex is a square complex with one vertex, steady knot, n plus n edges, m times n squares, such that the link in Y at the vertex V naught is isomorphic is the complete bipartite graph. In a BMW group, a BMW group is the phi 1 of a BMW complex, and Mn, my parameters, is called the order. So BMW complexes, so more generally, the square complex all of those links are complete by R-type graphs, are what anyways called complete complexes, CSC. And a very crucial fact, which is a lemma, I mean an exercise to show, is that if Y is a complete square complex, then the universal cover of Y is a product of two sheets. Okay. And in the special case of BMW complexes, so you know that it's a product of two regular trees whose degrees are given by the double of the parameters. Okay. So the next basic fact, which is also an exercise, so I will not draw on the blackboard BMW complexes. What I write on the blackboard is presentations of BMW groups. But from those presentations, we can recover the complex, right? And the basic fact underlying this is, again, a lemma, is that a group gamma is a BMW group if and only if gamma is torsion free and gamma has a Kiel graph isomorphic to the one skeleton of the product of two trees. Right? So this is one way to go just one dimension higher from free groups. You study, instead of studying groups having a Kelly graph that's a tree, you study groups having a Kelly graph that's a product of two trees.
Does that mean direct products of free groups are?
Yeah. So that's a very example 0. Gamma, the group on M plus n generators, A1 to M, X1 to M. And so I need M plus n generators and M times n relations. Okay? So that's a very nice set of M times n relations. And you see that the fact that my link condition is satisfied means that in all my relations, which are of length 4, I will see all possible corners between, one generator or its inverse and another generator or and its inverse. Okay, so So that's indeed isomorphic. So we are just looking at groups having a Kelly graph isomorphic to the Kelly graph, to the natural Kelly graph of that group.
Just as a graph, right? Not label.
As a graph, as an abstract graph, yeah, without, not a directed graph. yeah, if you start remembering the labeling, then. Okay, so example 1. What are BMW groups of order 1, 1? Well, yeah, one of them is Z plus Z, which is example 0. And then you have one more, which is AX.
Bimodal.
Yes, thank you. X, A inverse X, right? I1 to the kind bottom. And that's it. These are the only two. Two as more. So the next important concept is that of reducibility. So this is kind of the easiest example, and this is the next to easiest in the sense that up to a finite cover, it's reducible again. So this is what we want to define as a reducible BMW complex. So this BMW complex is reducible if it has a finite cover isomorph to the product of two graphs, and similarly, equivalently, a BMW group is reducible if it is virtually the product of two infinite free groups. Okay, but Z is a free group, right? So the next fact, which is, I would say, a proposition on cat-zero groups, says that a BMW, every BMW complex of order 1n is reducible. Okay, so if your Kelly graph is the product of a line and a tree, the group must virtually have a center, which is translates along the line factor. Okay? So gamma 1 and gamma 2 have order 2, 2, as you have. And so starting from 2, 2, you start getting irreducible examples. So that they are irreducible. Okay, so let me now sketch a little bit the history of history. As I said, so the study of those complexes was pioneered by B, M, and W, So I think Shahar Mozes was perhaps the first to construct irreducible explicit examples. And so what he produced in '92 was a family of examples. So for every p l primes congruent to 1 mod 4, I think. 1 mod 4. There exists an irreducible BMW group of orders p plus 1 over 2, l plus 1 over 2. And the group is a lattice, necessarily irreducible in PGF2 P cross PGF2. So Danny White, in his PhD thesis, yes, so yeah, I should. So for such an example, it's an irreducible lattice in a product of two rank 1 p-adic or algebraic groups of a local field. So you would be able to apply. You are in a setup where Margulis normal subgroup theorem applies, so you know that such groups are hereditarily just infinite by Margulis. So you get H, J, I, psi Margulis normal subgroup theorem. And I will come back to this tomorrow, next week. So why is Danny Wise in his thesis? So he showed that there exists a non-residue finite BMW group of all the free-flow. And I will recall his construction also a bit later. But this was kind of the first example of a cat-zero group, which is not reasonably finite, and also, because of these BMW presentations being of a special kind, they are actually small cancellation presentations, but at the limit where you get not necessarily hyperbolic groups. And so, in particular, you got the first small cancellation group, which is not reasonably finite, and this was a famous open problem at the time, but that predates hyperbolic groups. So I think it was a question of Schub in the 70s, whether such things exist. And also, as a consequence of that, there is this machinery that Gromov calls hyperbolization. So you can, starting with a compact cat-zero cell complex, there is a way to produce a manifold which retracts from the complex, and the manifold itself has a cellular structure, and it carries a locally cat-zero metric. Okay. So as a consequence, using Gromov plus, I think the details were written down by a guy called Hu. I don't know the first name. So from this it follows that there exists closed manifolds with a locally cat-zero metric and a non-finite fundamental group. And I've carefully written this sentence in that way. So from what I understand of this construction, you really get a manifold, and with a cell structure, which it gives you a locally cat-zero metric. But what you don't know a priori is whether you can actually find a Riemannian metric of non-positive curvature. And actually, I think it's by applying this kind of machinery that you produce examples of closed manifolds with a locally cat zero metric, but no, not a smoothable one, no Riemannian metric of non-positive curvature. So, and actually, I'm not quite sure about the status of this problem. So, do there examples? Do there exist examples of smooth, closed Riemannian manifold of non-positive curvature with a non-really finite?
So what's the dimension of the manifold?
Yeah, it will be much bigger than here. I don't know if you start with this, what's the dimension of that manifold? Yeah. It will increase a lot. So yeah, maybe some people know more about. So the question, what about NPC manifold? So NPC in the sense of. Okay. So, and then we have, of course, the heroes of my story, Burger and Mozes. I mean, Wise is another hero. So. The second and third heroes. So they have a note published in '97, and then the main papers were published in 2000. So they proved that for every n, m, at least 109, and for every n, at least 150, there exists a virtually simple BMW group over N. Okay. Now a bit later, Diego Rapagui, in 2004. So he did several things, but so he slightly improved earlier results. So he studied the construction by Shahar, and he produced similar examples for arbitrary pairs of distinct primes. So one thing he did is to generalize a Mozes arithmetic construction to any pair of odd primes. So that's what he did. One of the things he did on the arithmetic side, and he also improved a lot these norms, and also he showed that for all mn at least 5, there exists a virtually simple again, very good.
Virtually what?
Virtually simple.
Sorry.
Around the same time, other people looked at BMW groups, Kimberly Robertson. And so they are C-star algebraists, and they studied those groups with a motivation that I don't quite understand. But at the end of the day, I mean, but certainly a good one. But sorry.
I can give a comprehensible
Yeah.
half an hour introduction at some point.
That would be great. Yeah, you should explain it to me. But in particular, they include in their paper a list of all BMW complexes of order 2, 2. And so what they showed is that there exists exactly there are exactly 52 homeomorphism types of EMW complexities of all the tutus. Okay. And they also studied the possible isomorphisms between their fundamental groups. And you should be careful that, as it is the case for graphs, so two non-homeomorphic graphs can have this, of course, an isomorphic fundamental group. And here, our situation includes products of graphs. So we should expect, isomorphisms of the fundamental group that you don't see, and on the level of the complex. So they show that there are so the number of isomorphism classes of groups of all the tutu is 41, 42, or 43. You couldn't decide. Now, it turns out that in his thesis, Diego Ratagui also studied the list of groups of all the tutu. And also, although these guys communicated and they acknowledge each other, so Ratagui has a different list of not 42. But it's not a list of homeomorphism types. He was interested in something else. And if you compare the two lists, and actually it took me some time to be able to do it because they don't provide the corresponding list of the other guys, but they provide a computation of the abelianization. And if you look at the column giving you the abelianization of both lists, actually you can match pretty much all the rows of the table. And doing this, so I realized that Ratagui's computation implies that you have at least 50 of these, at least 50 of the 52 are reducible. Okay? But we know the last two, the remaining two are gamma 1 and gamma 2. And they didn't know about the Stix-Wdowina result because this was in 2013, so it was some time later. And gamma 2, we only investigated it this year. So. So we know that these two are irreducible. Okay, and then of course, now comes the Stix-Wdowina, 2013. And so they showed something again on the arithmetic side, but this time they allow identical prime. So for every q another prime power, there exists an irreducible EMW group of all the q plus 1 over 2, q plus 1 over 2, and it's a lattice necessarily irreducible is EGL2 FQT. So now it's in positive characteristic. And finally, yeah, so Nicolas Radu, 2017. So he again improved a little bit the bounds. So I will come back to this, but the fact that Ratagi was able to let the order from 100 or 150 down to 5 is by using Danny Wise's example. I will explain this. And now we have gamma 2. So Nicolas Radu showed that gamma 2 is irreducible. Not really finite. We observe that. And now you can then go down a little bit, and so you can have virtually simple examples starting from order 3, 4. And you can actually get 3, 3 if you allow torsion. You cannot do it with a BMW group in the strict sense, but you can do it. You can obtain groups. So scaly graph is the product of 2 trees, but you will have some elements of order 2.
Interchanging the trees, right?
No, not in so the Cayley graph is really the one skeleton of the product of the 2 trees. So every element of the group, it preserves each fiber. It must preserve every generator of the group preserve both the fibers.
Okay.
But what you can have is an element of order 2 swapping the 2 partitions of the canonical by swapping a vertex and its neighbor in each of the 3 factors.
Okay. Some people wouldn't call that the K graph. Because sometimes you think of the K graph as being like S.
You know, I like to think of
No, sure.
every regular tree is the Cayley graph of a free Coxer group, right?
It's whatever makes you
Can I can I give it to you?
Yes, can we just...
I can bring it next time if it's okay. I mean, yeah. It's a group on 7 generators and 12 relations. I think I brought a virtually simple one. So
Are you sure that's virtually?
I will not copy this presentation. I can give it to you. Okay, so now, I want to make an analogy. So we are working with a very specific family of groups. So it sounds like very restricted, but the history shows that it includes very different kinds of examples. Arithmetic groups in characteristic 0, characteristic in positive characteristic, and then much more exotic guys like virtually simple groups. And of course also products of free groups. Okay, so my analogy will be with real hyperbolic closed manifolds. So I want to mention the work of Patrick Gelander and Ariel Witt in 2014. So they showed the following: that n be at least 4, and CCN V be the number of commensurability classes of closed real hyperbolic n manifolds having a representative of volume at closed B. Is that clear? The definition? Okay. So you know there is a classical result due to one that you have only finitely many isometric classes of such manifolds of volume at most v. So you want to count them and to understand how fast this number grows with the volume. And here we count the number of commensurability classes. Okay, and what they prove is that this number is super exponential, so it grows super exponentially. So C and V is like between the V to the AV and the V to the BV for all V large enough. And there is another theorem due to Lipetsky, 2007, which says that the number of arithmetic ones is at most something which is almost polynomial.
Stupid question. Are those the same V in the exponent as in the bottom? Or are those
Yes. It's V to the V, basically.
Okay.
So you should think of this as V factorial. It's essentially V factorial. So V is a real number. If V is an integer, you should think of this being roughly, so it grows as fast as the factorial. So Lipetsky showed an almost polynomial bound for the arithmetic compact real Catholic manifold. And the conjecture is that it's really polynomial. So conjecture is that epsilon.
Epsilon equals 0.
0. Thank you. And he could show that epsilon equals 0 for the non-uniform lattices. But I want to focus on the non-compact manifold, finite volume. Okay, so my goal in my lectures would be to try to give evidence for a conjecture, which is that we'll have similar formulas, similar growth, in the realm of BMW complexes. So, conjecture. So let C BMW and be the number of commensurability classes of BMW group of all the n. So then, first, so we have the analog of the Gylander-Levy. So this should grow like n factorial. N or some AB. And 2, the number of arithmetic is at most polynomial.
So that's defined as a lattice in PGL. So PGL, I mean, so for example, the sticks-Dovina examples count as arithmetic, given that the field is-
Yeah. So even, I mean, here I could, instead of arithmetic, I could put linear.
Okay.
So we have a lower bound. We have a lower bound on commensurability. It's like q minus 1 divided by 2. So the lower bound.
Okay. So
Or it's m. What would be the prime? Because there was a prime involved q.
so q
Then
m is q plus 1 over 2. Is that right?
yes. So then the number of commensurability classes like it's q minus 1 divided by 2. So it's
It's linear.
Yeah.
So that's the theorem of sticks and Dovina.
Do you expect something very different if you count complete square complexes instead of or complete square fundamental groups?
Yeah, I mean, here so you see, you have to bound here. So in the manifold case, I fix the dimension and I let the volume grow.
Yeah.
Here, in a sense, I impose that all the actions are vertex transitive. So in a sense, it fixes the volume in a sense. But then I let the order grow.
I see. So,
Okay,
so
so
what
if I
so what should
allow
probably
things
fix the
that
number
have
of
a larger
vertices.
fundamental domain, yeah, I don't know.
So you could think about complete square complexes with some fixed number of vertices, but
Yeah.
if you let the number of vertices go through.
Mn.
Yeah, I mean, you can write a conjecture for Mn.
Okay.
I mean, here I take the homogeneous
Okay.
guy, just, yeah, you would have to modify slightly the function as a function of M. And then the lower bound is probably not known, or in general, for Mn. Okay, so, yeah, and so my goal will be to kind of give evidence for this conjecture in my lectures, and so. But I still believe that this is it's a long way to go to prove such things, because we don't know algorithms. So if you give me a BMW presentation, I have absolutely no algorithm to decide whether this complex is reducible, or this complex is has an arithmetic, as a linear fundamental group, or as a residually finite fundamental group. And of course, all these questions are highly relevant to the counting problem here. Okay. So what we do have are criteria, sufficient but not necessary conditions, ensuring that some of them are irreducible, some of them are not really finite. Okay. So I will explain that. So that will be, yeah, you know, the theme of forthcoming lectures. So I'll have a lecture. The next one will be on the just infinite property, okay. And that's where really it's absolutely crucial to consider non-discrete simple locally compact groups. So that's for next week. I'll have a lecture on residual finiteness, and here the key notion is subgroup separability. So that's a theme that's very important in manifold theory too. And I'll have a lecture on reducibility, and then probably I'll also use part of my time at the end to speak about groups whose Kelly graph is not a product of two trees, but another type of Euclidean building, to other types of Euclidean building. But for today, that's it.
Could you just the wise non-residually finite example? Does that actually only have finite evaluating finite equations, or have I misremembered?
No, it maps onto onto the infinity or onto Z. I mean, yeah.
Because he does have examples which have no finite quotient.
Yeah, but they are not. They are again. They are complete square complexes, but with more than one vertex. Yeah. Ah, and there is a Henry also pointed out to me last week that I should add on my history that Meenakshi Bhattacharjee, in her thesis in '92, she obtained the first example of I should have said this earlier. So, that's Bhattacharjee in '92 in her thesis. So there exists a group gamma, which is a suitably defined free amalgamated product of two free groups of rank 3 over a common index 6 subgroup, which is this 3 of rank 13. So this acts on the 6 valent tree. And if you define the amalgam properly, she proved that gamma has no finite quotient. Okay.
So by finding, so you're just doubling along this?
No, it's not doubling. It's not
doubling. Okay.
So not
it's from the same.
doubling. So the two
Are different.
the two injections are very, very different. But Henry asked me, by the way, maybe she has the first example of a squared complex whose fundamental group has no finite quotient. So I looked at the paper, but how does she prove that her groups have no finite quotient? She arranges the amalgam in such a way that some of the generator in gamma, some generator A is such that the fifth power of A is conjugate to the square root. Okay. So that's a good thing to know if you want to exclude finite quotient. It means a BS25 maps onto your group, and BS25 is not really finite. So you're on a good track once you have this. But this prevents your group from being a cat zero group. So gamma is not.
So if we're going back in history, then a student of Graham Higman in the early 50s, Ruth Cam, she did a similar thing, F4, but it's over a non-finitely generated amalgam.
Right.
And that she showed that was simple.
Yeah.
So, but it's not. But the resulting group is not finitely presented.
In 53,
Yeah, I think so. Yeah.
I mean, she obtained infinitely many non-isomorphic finitely related simply groups. I think even uncountably many.
Yeah.
But they act on a tree of infinite valence. Thank you.
Disappointed I won't be here next week.